Did I share the screen?
Okay, very good. Yeah, let's go ahead and get started. And Ada, I'll let you introduce the topic and we'll learn some great things.
Sounds good. Hi, everyone. Hi, GDG Silicon Slopes. I'm really excited to come today and give a speech, give a talk about recomposition in Android apps. Recomposition usually means there is a, think of it in a light form, think of it as an invalidation of all the UI elements all over again in Jetpack Compose. So, a little bit about me. I'm an Android GDE, software engineer at Twitter, and also an instructor for the Udacity Android Developer Kotlin course. And here's the list of my social media channels. So, what is in today's agenda? Today, we're going to be talking more about what is Jetpack Compose exactly in terms of Android. We will deep dive in the foundation of the Jetpack Compose to understand what's the big deal about it and why is it so different from the traditional Android. And then from there, we go into what is recomposition, understand what is smart recomposition, what's the difference between smart recomposition and regular recomposition. And then we also learn a little bit more about practical tips that we can use, to leverage this recomposition, and then learn more about the tools to debug, detect this recomposition. So historically, Android views are represented as a tree of digits, right? Where in order to update one element, you would need to go through the tree, find that node, pass the new argument via exposed getters and setters, and update the internal value of that UI widget. But that approach was prone to errors. For example, by the time you find that node in the tree to update the value, the node might have been removed already from the tree, right? And then this would throw an error on this. It would throw an exception. Jetpack Compose, on the other hand, is a declarative UI framework, meaning UI widgets are functions instead of being an object. There is no internal state being held. And the only way to trigger the updates is by passing different arguments to these functions. And Jetpack Compose has built this substantial machinery to detect those different arguments and trigger updates not only in terms of single composable function, but the entire app. So how does this machinery work? Let me give you an overview of the most important parts of it. Android OS is built as a tree of widgets. So nothing on that end actually changes because Android operating system is still tree of widgets. Unlike Jetpack Compose. Jetpack Compose has a state snapshot system in place that communicates directly to Android OS via observers and subscribe to all the user interactions that usually drive a change in the state, hence the state name in the state snapshot system. All of those changes are passed down to composition, where composer produces the next list of changes based on the information inside the slot table. Slot table, it is in-memory cache that contains the latest and up-to-date information about the composition. Once the composer produces the change list, it records the information back to the slot table and applies the changes to the UI node 3 that in return gets reattached to the Android OS. So that's how Jetpack Compose works in a nutshell, in a very high overview. So let's dive into the foundation and get better understanding of how recomposition works in Jetpack Compose. When we talk about rendering UI widgets and seeing the final results on the screen, it is important to keep in mind the phases each widget goes through. In Jetpack Compose, we have 3 phases. The first one is a composition phase that is responsible for a question, what UI to show? It essentially creates a description of the UI. The second phase is a layout phase. Answers the question where to place UI. It measures and places all the child nodes in a single pass. This is where modifier functions from Jetpack Compose come into play. And the third phase is a drawing. Answers the question how it renders, right? Basically, it draws all the UI elements on the screen. The order is always preserved, although some sections may be skipped. Here's a big note on it, because later we will discuss what phases can be skipped during the recomposition. So within these three phases, Jetpack Compose has also its own layers, where every layer is responsible for a specific part. Important to note, these layers are represented as a separate modules in Android. Runtime and compiler are the hearts of the Compose and responsible for running this declarative machinery in place. And they are platform agnostic, meaning as long as you write your own UI layer, based on the web support or iOS support, you can use this runtime and compiler, use this Compose machinery, and make your own Jetpack Compose applications for web, iOS, and so on. UI layer is an essential communicator between Android OS and the Compose world. It is aware of Android lifecycle, instance changes, context, accessibility, and so on. Because UI layer is an integration layer between Android platform and the Compose world, it is also responsible for executing all of those composable functions. And it's done via setContent Lambda function. On the other hand, it is also responsible for passing down all the platform-specific information like context, keyboard state, lifecycle, save state instance, and so on, as a composition locals down to the runtime. After the set content is called and all the relevant platform information is passed down to runtime, Compose phases and layers begin to play in runtime. This is where composition phase begins. Runtime is a vital component of Jetpack Compose that contains all the logic and execution. And within runtime, there are three important classes to keep in mind when it comes to composition. First one being composition class. Note, it is different from the composition phase. Composition class contains slot table, composer, change list, and so on. And the constructor of composition class expects recomposer class and the applier class. Recomposer contains the state snapshot system and list of composition classes. Applier is an interface that is responsible for materializing UI and seeing the final result on the screen. So let's take a look at the recomposer and learn what is its job in the composition phase. When we think of recomposer, we should think of it as a scheduler that is responsible for triggering, awakening the composition phase, and passing down the updates to the list of compositions. And because recomposer contains the state snapshot system that observes OS changes, in the UI layer, we have a window recomposer file that initializes that lifecycle-aware recomposer. The initialization happens in Android's view extension function. And because it is Android's view, we can locate the lifecycle owner of the view and attach the lifecycle observer. Notice in this code snippet, in onCreate event, recomposer call a function run recompose and apply changes. This function registers an observer for the change propagation. When that happens, this observer awakes and adds all the changes to the snapshot system that ends up passing down the changes to composers so they can record what parts of composition need to be updated. In other words, this observer is the first step for triggering automatic recomposition when the state changes. So what does state snapshot system exactly do? It captures results at a specific read moment. Jetpack Compose compiler wraps all the composable declarations and expressions to automatically track snapshot read state within the bodies. This is how snapshot state is observed. The goal is that every time the state read varies, the runtime can invalidate all the composables recompose scopes, so it's executed in the next recomposition, which means recompose. To visualize the state snapshot, let's have a composable function state snapshot system that contains two states: the name, which is a mutable state of string, and is important, which is a mutable state of Boolean, right? Type of Boolean. And then the state snapshot system function contains column. Within the column, there is checkbox and the text. Let's assume we went through the first three phases of composition, layout, and draw, and we finally see the final result on our screen. Then we decide to toggle back and forth the checkbox. Recomposer has awakened because it noticed the user interaction, and the state reading happens. When the state reading happens, because we changed the value inside the state of the on-check change listener from is important value equals exclamation mark is important value, the state snapshot system read two values for the state is important, right? True and then false, and read one value for the state name. Then all the state read results are propagated to the list of composition classes, where Composer identifies changed versus unchanged values in the states, and then updates the slots and the change list. So what is composition class in this example? Composition, it is a process of executing those composable functions by storing them and the relevant information on the slot table. Upon initial composition and applying changes to the slot table and UI node 3 upon recomposition. When we mention something about executing composable functions, it is also important to keep in mind it is more of storing the latest state information rather than executing and seeing the changes on the screen right away. So in set content function, the entrance to the Jetpack world, when recomposer is initialized, applier and composition classes are initialized too. Note, recomposer and applier are arguments of the composition class. So what is composer? Think of it as a manager that knows when to read, when to write to the slot table, when to produce change lists, how to produce change lists. Composer itself is an interface that helps the compiler to talk to the runtime. So essentially, it is a middleman between runtime and compiler. What is slot table? We talk a lot about slot table. Slot table is in-memory representation. It's memory cache flattened array that gets filled within relevant information upon initial composition, then gets updated upon recomposition, and then contains the latest state of the composition. It is important to note about the latest and the current state, because later on, when the recomposition happens and the change list is produced by reading the slot table and understanding the state of it and comparing the new list of changes. So slot table not only contains information about UI widgets, widget functions, right? But also about all the parameters, sources, the location, and so on. And because slot table is a representation of the current state, let's take a look how it gets filled within the information upon initial composition. Let's take a look. We have here a simple composable function card that has a column with a text in it and the button. Within button, there is a text also, click me. Once we call it composable, the composition actually creates a flat array with empty slots. Representation of the gap buffer, what it means is that it creates a array with more available slots than it needs to. So it can always fill up later on. Once the function card is called, Compose actually creates a group and takes up the spot in the slot, group 1, 2, 3. Then we have a column. Because column actually accepts other composable functions as a content, Composer creates a group for it as well too, group 4, 5, 6. And within column, we have two composable functions, text and button, right? Text, as you see, gets filled in the slot table as well, but because it does not accept a composable function as a content, as a parameter, what happens is text actually ends up being a regular function with the value in it, rather than being a group.
Oh, there we go. I just couldn't see the slides at first, but now they're back.
And then we also have button. Because button accepts groups, right? Accepts parameter, composable functions as a parameter. There's a text inside the button. We create a group. Composer creates a group 7, 8, 9. And then also on-click listener is added to this flattened array and taking up space in the slot table. And then here we also have a text, again, with a value click me kept inside. So it is important to keep in mind that slot table only records the changes, to get to the latest state. It doesn't actually display it. The composer reads the slot table and produces the change list based on the information in it. And each change is deferred action with access to the slot writer and the applier, waiting to be executed. So it's deferred action, not an actual execution happening there. After the change list is produced, all of those deferred actions will start executing, meaning slot writer will write in the slot table all the newest changes so that slot table contains the latest state. Applier will apply all the changes in a batch to the tree. So applier is responsible for measuring, layout, and drawing UI widgets. Once applier begins its work, the layout phase starts. So applier is an interface for materializing UI 3. Because applier is an interface inside the runtime, UI layer contains an implementation of it, and it's called UI applier. In layout phase, we have another in-memory data structure. And there are 4 steps in the layout phase. The first one being we have to add child nodes bottom up to the root. So we start with the inner text, click me, right? That gets attached to the button. Then button to the column, and then column gets attached to the root node. Then after all the elements actually attached up to the node, begin measuring child nodes. But in order to measure the child nodes, the root node has to pass on all constraints like padding information about the parent, right, that parent contains, like margin information and so on. Once child node receives all the constraints, it measures itself and then lets the parent node goes up in the chain to notify about its sizes so that later on the parent node, can define its own size. And then the last 4th step during the layout phase is placing all of those child nodes on the screen. And the last phase, drawing, right? Well, what happens is the screen gets rendered with the newest information, and we see the update. After drawing is completed, that change list that was produced, and change list was produced, which is a deferred action, right, between keeping the latest information in slot table and updating the UI tree, it gets cleared out. And so we get this final result of the text, button, and the text inside. So what is recomposition? In imperative UI model, to change a widget, you would call a setter on the widget that will change its internal state. Like, for example, button set text, and you pass a new value, which internally would change a value of the text state that is inside the button. In Compose, you call the composable function again with the new data. Doing so causes the function to be recomposed. The widgets emitted by the functions are redrawn if necessary with the new data. The Compose framework can intelligently recompose only the components that have changed. And so recomposition is a recalculation of all the changes necessary for the composition state that is held in the slot table and materialized tree, which applier is responsible for, and scheduling all of those changes. And so we have in this diagram, one thing to keep in mind is, because initial composition goes through all of those phases, what happens with recomposition? It starts over and starts with composition, layout, and drawing. To further display this recomposition process, let's look at the example where inside this card we introduce a counter, right? Counter that counts the values. And the value of the counter is read inside the inner text of the button, right? So let's actually click on the counter and see if our text actually updates the value and if we notice recomposition. One thing to note is event handlers like buttons on click, even though they take up space in a slot table, they're not composables and they're just regular functions. And whenever this click handler is invoked by the framework, it is done so outside of any recompose scope. Therefore, nothing changes. But once the click happens, we are updating the counter value, which means the state slot that we have reserved for the state gets updated with a new value 1. And then click me gets updated as well too. Click me 1, because it is reading the state right there inside the text. What about the second example? Let's read the same state, not inside the inner text, but in the outer text, right? So we have compose counter. Right now we have state 0, and the compose text with 0 is there too. So again, when the click happens, what kind of changes we see? Once the click happens, the state value does get updated, right, inside the slot table. But if you noticed, the group 789, also the compose group 789, which is a column, then compose 1, which is a text itself that reads the value of the counter, gets updated. And then group 101, which is a button, gets updated. However, the inner text inside the button doesn't get updated. So Jetpack Compose can intelligently detect parts that have changed, but whenever it detects, it also notifies the nearest parent scope, right? In our example, because it's a text, outer text, the nearest parent scope is a column. It notifies the column saying something has changed. Can you please update your children? So what the scope, the nearest parent scope does is it updates text and button. But because button itself is a group, and it knows that nothing has changed inside the button, the text inside the button doesn't get recomposed. So recomposition goes through the same steps of updating the slot table, generating the change list, updating the node tree, measuring, placing, drawing UI elements, and attaching the newly generated tree to the view, which is potentially expensive in terms of time, computing power, and battery usage. And to mitigate this cost, Compose intelligently chooses which parts are needed to be updated at any given time. And it's possible via smart recomposition. So smart recomposition is an intelligent way to skip the recomposition of composable functions when their inputs are stable. So runtime has a defined set of rules to help compiler detect this smart recomposition. Rule number 1, making sure that the result of calls to equal of two instances are the same. Rule number 2, when a public property changes, composition is always not notified. Rule number 3, all the public properties of the type have to be stable. So what do we mean by stable, right? It's stable is a marker, custom marker for compiler to know when to trigger recomposition, when not. And there are some predefined stable property types that compiler knows right off the bat. The first one is being primitive types, like integers, booleans, characters, float, and so on. All the primitive types is marked as a stable type for a compiler. Second one is a string. String is not primitive type, but at least it's immutable, and then therefore compiler thinks of it as a stable property type because you cannot modify it. And then there's a third type, any kind of data type that is annotated with @stable marker. One note here to keep in mind is do not overuse @stable marker because it can be costly, especially when it comes to like debugging the issues. Once your app goes to production, it's going to be really hard to debug down the issue. It will come down to the compiler to understand what exactly is happening there. So it's always better to leverage the existing mechanism and ways to skip some of those recompositions and have stable types. But what about custom data types? Because we developers don't really use the primitive and string types all the time, right? So we have our custom types. And for that, Jetpack Compose, especially runtime, has an inferring class stability algorithm that visits each eligible class and annotates it with @stability inferred. Basically helps compiler to determine what to recompose. I mentioned that it visits each eligible class. Here's a list of some ineligible classes, like enums, enum entries, interfaces, and so on are not considered eligible classes. So interfaces are not eligible is because collections, there is no guarantee that some of the collections can be mutable, some of them can be immutable. And because of that, because compiler right now, Jetpack compiler, still in active development and still does not have, still in active development, everything is still in work in progress. What they did is they followed the Kotlin compiler rules and decided that all the collections are considered unstable because we don't know the implementation details of it, because it can be implemented different ways, right? Can be mutable or can be immutable. It's also again worth noting that Jetpack Compose in active development and more simple types will be added to compiler later on. So to learn and understand the recomposition better. The first one being recompose highlighter. This is the modifier function that Google Play team came up with. What it does is whenever you have a, let's say, lazy column or any kind of app, and you're listening to the changes in specific UI composable function, you can add this modifier function to see how many times your UI function actually being recomposed. Where in this example, blue means it was recomposed 1 time, green means it was recomposed 2 times, yellow means it was recomposed 3 times, and then red means being recomposed more than 3 times. Also in May, Android Studio Electric Eel announced the automatic support for the recompose highlighter, which I'm really excited about that, but it's still in beta, and it didn't reach the beta yet. It's before beta right now. Number 2, it's an ancient and most reliable. This is something that I've used to analyze and research more about recomposition, how it works exactly. Basically, what happens is it just prints out the logs about how many times each composable function was recomposed. I actually modified the compose highlighter and made a modifier function out of this print log statement, where I can pass a calling type, calling composable function, and I will know exactly how many times this specific composable function was recomposed. But if you really want to have a full-blown analysis of recomposition, composition, and entire Jetpack Compose app, I recommend to use Compose Compiler Metrics, because it will give you full analysis, and it will spit out a JSON format, JSON file with a list of skippable, restartable, read-only, or and total composable functions that will give you better understanding. Also, it's important to note that if you, in this example, for example, we have a difference between restartable composable functions and skippable. We see restartable 76, but the skippable is 64. What it usually means by its names, it means there are 76 composable functions that can restart at any time, at any point, whenever the inputs are changed. But then only 64 that can be skipped, right? So if inputs have not changed, it means only 64 can be skipped, which means there are 12 composable functions, but essentially keep getting restarted, even though the inputs have not changed. This kind of full-blown analysis, Compose Compiler Metrics can give it to you. And then, as you see in previous 2 slides and in this one, I've also added a link to the code snippets, for see the code example or integration details of how it could be done. And as you saw in the smart recomposition section, Compose naturally tries to avoid unnecessary work and unnecessary recompositions that will cause to repeat the phases all over again. But to help the Compose even further, we developers can use some tips to leverage smart recomposition. Tip number 1, breaking down composable functions. There are different ways to structure your functions. You can decide to put all of your composable functions in a nested way, or you can decide to have more flattened way, and so on. But the more you break down, the more you reduce the recomposer scope, meaning the number of recomposed functions will get reduced. Here's a simple example of the column that has 2 columns inside, right? And each column contains a text and a button with a text. There are multiple ways to structure this simple screen, but the most optimal one is to have a separate composable function, like here's the greeting, right? Because that way you will be able to reduce the recomposer scope. Number 2, using the key composable. So Runtime assigns a type, to every group in the composition. If you remember in the slot table, we saw composer created group 1, 2, 3, 4, 5, 6, and a 101, right? And each group has a type, specific type, whether it's restartable, replaceable, or movable, right? When the key is not set in each group, runtime cannot determine whether the item in that list was changed, the value inside that item was changed, or the item itself was just moved. So by setting the key, a unique key, runtime lets compiler to know about the unique hash code for each item, therefore prevents the recomposition of all children and recomposes only changed ones. Here's an example where we have a list of fruits, for example, where we remove a strawberry. If we don't set the key, what happens is everything below the strawberry, like banana and blueberry, gets recomposed as well, right after we remove the strawberry. Although the inner values, the inputs of blueberry and banana have not changed. So whenever we set the key, as you see in this with the highlighter example, the blueberry and banana don't get recomposed even if the strawberry is removed. Number 3, reading the state value at the lowest composable function. So by deferring the state read all the way down to the actual consumer, the child node of the state, runtime will recompose only that function and not the parent and subsequent parents of it. Here's the example where we have a Android and then Jetpack Compose view system column inside the row, which is inside the column, right? And whenever we change the value of the card info, we have a view system and the Jetpack Compose keeps getting updated. There are multiple ways to do that by passing down the changed value, which is either Jetpack Compose or Android, Jetpack Compose or view system, passing down that value straight to the good row, right? Good row function, or like reading step 3. But once we pass down, what it means is we end up reading, recomposing not only that inner column because the value changes there, but it's also we're recomposing a image that didn't get changed, right? So that's where like reading that actual value at the lowest composable function is important. Number 4, using modifier lambdas. So whenever a state's value is passed down to modifier's regular functions, right, and the read happens right at that moment, it usually causes the nearest scope to recompose. And when a state's value passed down to the modifier's lambda function, the read is deferred until the compose reaches the layout and the drawing phases based on the modifier's type. Here's the example of the modifier offset, right? We have a y-axis parameter that frequently gets updated because we're moving this composable function up and down. If we keep a regular modifier function offset, what happens is because the y-axis value is frequently changed, it recomposes entire row all the time with every frame move. But because we use lambda, we're deferring the read up until the modifier functions come in play, which happens in the layout phase. And number 5, utilizing derived state of. Most of the cases, especially on UI, we have some sort of object, that depends on the certain state object, which is frequently changed. And all the composable functions listening to that object, will recompose more than they need to. So it's always better to wrap that kind of object in the derived state of function to limit the number of recompositions. Here's the example. Here we have a height bottom bar object, right, that is listening to the that gets updated whenever the list is scrolled or not. So with checking whether the list state is in scroll progress or not. And whenever it gets updated, whenever the scroll happens, our bottom bar actually disappears to have a full immersive experience of the list, and then appears back up whenever user stops scrolling. As you see, this is a very frequent changes happening within the list state itself. And if we don't wrap the height bottom bar with the right state of, what happens is our bottom bar keeps getting recomposed on every frame change. And all these changes keep getting scheduled, over and over again. And so number 6, I think there are some tips worth repeating over again when it comes to composition and recomposition in Jetpack Compose. Tip number 1 is make sure there are no logic inside the composable functions, especially any kind of expensive work. All the logic, move them to the view models, presenters, and so on, so that your composable functions can just consume some kind of UI state, the latest information from it. Number 2, do not create dependable composable functions, because the result, the order of execution is never guaranteed. So let's say you have a global variable, hello, like string global variable, where you update its value in composition 1, but then you read that value in composition 2. There is no guarantee by runtime or compiler, there's no guarantee that the composable function 1 will be executed first, and your value to this hello string will be set before the read happens in the composable function 2. So that's something to always keep in mind. And number 3, side effects. Avoid any side effects in the composable functions. It is again because not only composable functions can run in any order, they can run in parallel, meaning runtime, especially a recomposer, can decide what thread to execute and schedule the recompositions. So the invocation basically might happen in completely different thread than a caller. And for this kind of examples, it's always better to use callbacks. And so this was a recomposition talk in Jetpack Compose. Hope it was helpful. Thank you so much for having me, guys.
Aida, thank you so much for all that information and the links and code examples. Yeah, do you have a few minutes if people here have questions to stick around? Okay, yeah, let's see if anyone has a question that they'd like to share or ask.
So I have a question for you. Drag and drop, is that very doable in Compose?
Yes,
so let's say you have a list of items you want to be able to reorder them. How do you do that in Compose?
So in Compose, we have a modifier function called pointer input, if I remember correctly, that is responsible for specifically drag and dropping the elements, from the list column to the okay. Sorry, guys, to drag and drop elements in the column or like in kind of row and change the positions. For this example, I recommend to use the key composable function, right? So then you can set the unique key instead of relying on the element's position.
So using keys, okay.
Let me find exact name, pointer input, if I remember correctly. Pointer input modifier function. Yes, pointer input. That is responsible basically. Okay, gestures are there, and then drag and drop was there too, if I remember correctly. Yes. Yes, detect drag gestures is there too.
What can you put in the chat? What is it called?
It's called pointer input. Let me put it. Pointer modifier function. Okay. So it has all this like where you can detect the gestures happening. You can also do the swipeable, swipe is available right there.
So can you do this? Let's say you have like kind of like a view pager type action where you swipe between them. Does that work with this too?
So the view page part.
So here you're scrolling left to right, but you want to go back and forth. So let's say you have an infinite calendar you want to do.
Yep. So that's something I haven't tried yet. And I'm pretty sure it might cause we might need to do some custom calculation, right? To making sure.
So there's an accompanist library that can handle view paging.
But can it do like an infinite type?
Believe so. I mean, the one they're showing on that doc is for images, so.
Oh, okay. Horizontal pager.
But
Yep.
like you have to set a count and whatnot. So, I mean, you couldn't really necessarily do infinite, but I'm sure there's ways you could get around it.
Yeah, I've been trying to do that for many years. Never really found a good solution to it.
I mean, if your count is based off of a paging library, then technically, and you could technically update the count as you scroll.
Yeah, I saw someone do something like that. Basically, they modified which one they were on as you scrolled.
Mm-hmm.
So there was like 0, 1, and 2, and they're always on 1. Yeah. Okay.
That's interesting.
Yeah, the accompanist libraries are pretty cool. There's a lot.
Okay.
Yes, accompanist is really cool.
I have not used those. I've been doing wearables for the last year and a half, and Compose was not ready when I tried to do it a year ago for wearables. But apparently it's getting better, so I think they're going to try again. But my contract ends at the end of the month, so I probably won't be the one to do it.
Compose actually OS right now is in beta. It went beta this May.
Yeah, for the wearables.
Yes. I think if I remember correctly, it's called Horologist.
Yeah.
Yeah, but they wouldn't. Yeah, I did it a year ago, and they're like, "No, it's not ready for wearables yet." Undo it.
Yeah, Compose is good now on wearables, and the accompanist equivalent in Wear OS, as Ada said, is Horologist.
Wow. What's this horologist, Michael?
That's what we were just talking about.
That's what Mitchell was talking about. Yeah.
It means, so horologist is a watchmaker.
Oh.
Yeah. So, it's a list of all the sample apps that can be used on the Wear OS on the watch. It's for good examples.
Okay. So this looks actually really up to date with what the latest is. Yeah, it even has the picker on it. Yeah, you have to use a special recycler view. Yeah, they might have here. Oh, yeah.
I know they have a recycler view a lazy list in Wear OS that it will scale the stuff as it gets closer to the middle of the screen.
Wearable recycle view.
Yep.
Yeah, it kind of fades it out a little bit. Yep.
Yep.
Yeah, one of the hard things on the picker though is changing the style. from the values they give you. This is interesting. I'll have to take a look at it.
Technically, now with the Compose, changing the styles should be easily done via modifier. Although I say technically because it's never easy on Android to make any non-trivial change.
Yeah, I know. I'm curious on how they do that because the ones that toggle. Yep. I've been doing some stuff with pickers recently, and the buttons.
Another question for you, Ada. Are the slides something that we could post at some point in the future to share out your slides?
Yes, I published them. I can send you a link.
Okay. Yeah. Then, yeah, later after this meeting or the next day or two, we could attach them to the event page and people can review those. Do we have any other questions for the group or for Aida regarding Compose? I think it's been very helpful, very informative, and a great deep dive.
There is also one thing to note, since we're talking about the Wear OS, is that the UI layer, right, for the regular Jetpack Compose, which is Jetpack Compose itself, right, and the Wear OS basically is built on top of that Jetpack Compose, and then there's always going to be a sort of a catch-up game with the latest Android OS versioning, something to keep in mind when it comes to the Wear OS specifically. But last I heard, they promised an active, up-to-date Wear OS, with the Android OS system as well.
Cool. They even showed a little curved time on the top in this project. See how they have the time on the top of that player screen in the media section? It's curved. Well, it's interesting though. Thanks for talking to us about how when it redraws and everything, that can be expensive.
Yeah.
Yep. Sometimes it's always interesting to know what exactly happening behind the scenes, to get a peek of it and learn a bit more about that.
Yeah. That is great. Yeah, I think it's going to be better as I get more familiar with Compose. Well, thanks for coming. I'm going to sign off now, but it's nice seeing everybody.
Yeah. Yeah. Thanks for coming. Thanks, Ada, for your knowledge and presentation. Yeah, that's great. Thank you so much.
Thank you so much for having me, guys. It was a pleasure. If you have questions, please shoot my way. My Twitter, email, Mike knows my email in case you need to ask more questions.
Yeah, they're on your slides. So.
Cool. There you go. Awesome.
Perfect.
Thanks. Bye.
Thanks so much. Thanks, everyone.